In the previous module, we have discussed an introductory methods of discriminant analysis and classification. We have seen how we can devise rules by which we can discriminate between different groups and then classify new individuals into one of these groups. Now, we have used two different techniques for doing this. The first was the minimization of the total probability of misclassification, and the second was the minimization of the expected cost of misclassification. We also saw how we can actually apply this to a problem where we had two exponential distributions and we were classifying individuals coming from one or the other of the two groups defined by this two distinct distributions. What we'll do in today's module would be to look at a very common problem of two normal populations and distinguishing between these two populations. So we'll have multivariate normal distributions where observations come from one of the normal populations or the other of the normal populations, and what we would like to do is to find a discriminating rule which would allow us to discriminate between the two populations and to assign new individuals into one of the two groups. Let us look into the problem of classifying individuals into one of two normal populations. Suppose there are m characteristics. M is, this is given by x1, x2, xm, which forms the x vector. These are to be classified into one of two groups, G1 or G2. G1 is characterized by f1x, which follows the normal distribution with mean mu1 and variance sigma 1. G2 is characterized by f2x, which follows the normal distribution again with a different mean mu2, and sigma 2 is the dispersion matrix. The prior probabilities of the two groups are P1 for the group G1 and P2 for the second group G2. The misclassification costs associated with the two groups are C2 given 1 for group 1 and C1 given 2 for group 2. The problem is to find a rule by which an individual can be identified with one of the two groups, G1 or G2. That is, to place this individual into either the first normal population group or the second normal population group. We first begin by looking at a classification rule when the two dispersion matrices are the same. That is, sigma 1 is equal to sigma 2. Let the common value of this be sigma. Now the density function for group Gj, j equal to 1, 2, that is for groups G1 and G2, is given by the usual normal density, which is fjx. What we need to look at here is the ratio of the two densities, one for the first group divided by the second from the second group. This ratio is given by f1x by f2x is exponential to the power of minus half x minus mu1 prime sigma inverse x minus mu1 plus half x minus mu2 prime sigma inverse x minus mu2. On simplification, this ratio comes out to be in a much shorter form, which is exponential mu1 minus mu2 prime sigma inverse x minus half mu1 minus mu2 prime sigma inverse mu1 plus mu2. So the classification rule based on the expected cost of misclassification is given by R1 if mu1 minus mu2 prime sigma inverse x minus half mu1 prime mu2 prime sigma inverse mu1 plus mu2 is greater than or equal to log of C1 given 2 P2 divided by C2 given 1 P1. And of course R2 would be just the complement set in this case. Now the rule you can see is based on the discriminant function, which we'll call z, and which is given by a prime x is mu1 minus mu2 prime sigma inverse x, where a is defined as sigma inverse mu1 minus mu2. So obviously a prime is mu1 minus mu2 prime sigma inverse. That into x gives you z. You can see that this discriminant function is linear in x. Why is this referred to as the discriminant function? If you go back and look at R1 or R2, you will see that z is the first term on the left hand side, and that is the only term which involves x. The second term on the left hand side is independent of x. It just depends on the parameters, and hence is given the parameters is known. Similarly, the right hand side is known, so everything besides x is known. So the first function is the only function that involves an unknown x, and the classification rule is based on this. So we call this function the discriminant function, and in this case you see that this is linear in x. Suppose the parameters mu1, mu2 and sigma are unknown. This is very often the case because we may not know mu1, mu2 and sigma beforehand. So what do you do in this case? We obviously need to estimate these parameters. We take n1 observations, say capital X1, which forms a matrix. This is n1 observations from the first group, and we take n2 observations independently from the second group. And then what we do is we compute the difference statistic from these two sets of observations. The statistics that we need are firstly the means of these two groups. So we get mu1 hat, which is x1 bar, which is the average of the first group observations. Similarly, mu2 hat is the average of the second group observations. We then calculate the dispersion matrices of the two groups. S1 square is the dispersion matrix or the sample dispersion matrix of the first group, and S2 square is the sample dispersion matrix of the second group. But remember that sigma 1 is equal to sigma 2, that is the two dispersion matrices are equal, but obviously the sample dispersion matrices would be different, but we need to pool these two. So what we get is the pooled variance or the pooled dispersion matrix as S equal to a combination of S1, S2 properly weighted. So this gives us the pooled variance S. And then the classification rule with unknown parameters. These unknown parameters can be substituted by the statistics corresponding to them. So instead of mu1, we have mu1 hat, which is x1 bar, mu2 is replaced by x2 bar, and sigma by s, and we go back to the same type of rules, except that now we have x1 bar, x2 bar and s instead of mu1, mu2 and sigma. In this case, the discriminant function would be z is equal to x1 bar minus x2 bar prime s inverse x. And again, as before, the first part of this is denoted by a, so it's a prime x. Now in this case, we have an alternative representation of the discriminant function. How do you get this alternative representation? Notice that z is equal to a prime x means a prime x1 bar can be represented by z1 bar. And this is x1 bar minus x2 bar prime s inverse, and the last x is replaced by x1 bar. Similarly, we can define z2 bar as a prime x2 bar, which is x1 bar minus x2 bar prime S inverse x2 bar. If we do this, then writing D as half of x1 bar minus x2 bar prime S inverse x1 plus bar plus x2 bar, this is equal to half of z1 bar plus z2 bar. Notice what D is. Note D is basically the second term on the left hand side of the rules. Okay. So what does the rules reduce to in this case? The R1 reduced to Z minus D greater than log of the right hand side. Or if you take D to the right hand side, is basically the discriminant function Z on the left hand side greater than or equal to D plus log of the ratio of the cost and the ratio of the prior probabilities. So we get R2 otherwise. So you now can formulate the whole thing in terms of the linear discriminant function Z. Let's look at an example. Suppose we have admission data for applicants to a business school, and our objective is to use the GPA and the GMAT scores to predict the likelihood of admission of a student. We have two groups. The first group obviously is the admitted group, and the second group is the group of students who have not been admitted to the school. And we have scores in GPA, which is x1, and in GMAT x2. So our m is equal to 2 in this case. We have two variables to look at, and we have 31 students in the first group and 54 students in the second group. So there were 85 applicants, of whom 31 admitted and 54 were not admitted. And this is how the data look like. Okay, so the red ones are those who have not been admitted, and the black ones are those who have been admitted. Obviously the black ones are on the right hand side. They have a higher GPA and GMAT score, and therefore they have a higher chance of getting admission. Now if we summarize this data and try and find a linear discriminant function which would distinguish between the two groups, we have the prior probabilities of G1. Since 31 out of the 85 have been admitted, so P1 must be equal to 31 by 85, which is 0.36. Similarly, G2 is 54 by 85, which is 0.635. Of course, P2 could have been obtained by taking 1 minus P1. In this case, the costs of misclassifications are the same, because whether admitted or not admitted, if you misclassify, assume that there is no difference in the two costs. The linear discriminant function on working this out comes out to be Z is minus 2.94 GPA minus 0.011 GMAT. So this function actually distinguishes between the two groups. And this function defines the two groups which has this following characteristic. The first group of admitted students have a mean GPA of 3.4 and a mean GMAT score of 561.22, whereas the second group of not admitted students have a mean GPA of 2.72 and a mean GMAT score of 446.67. So the linear discriminant function actually separates the space into two halves. So it draws a line, it's a linear function, therefore it draws a line between the two groups. And in the first group you have the admitted students, and in the second group you have the not admitted students. Notice that there are 3 red A marks in the plot. This corresponds to admitted students who have been misclassified as not admitted. So this sort of misclassification is what we try to minimize. So the better the rule, the better is the discrimination. But if you see this line here, if you shift the line a little downwards, probably all the A's would go into the blue region, but then some of the N's would also go into the blue region. So with a linear discriminant function, you may not always be able to distinguish correctly all the observations. There would be some misclassification, and the aim should be to minimize the misclassifications as far as possible. Now let us look at a classification rule where the dispersion matrices are different. The method in this case would be similar, and we'll define eta as this function here, which involves only the parameters mu and sigma. Once you have defined this eta, the minimum ECM rule by the same method that we did before gives us R1 as minus half x prime sigma 1 inverse minus sigma 2 inverse into x plus mu 1 prime sigma 1 inverse minus mu 2 prime sigma 2 inverse into x minus eta, which is greater than or equal to log of the ratio of the cost and the ratio of the prior probabilities, and R2 is again the complementary set. Now if you look at these two, observe something. Observe that you have a discriminant function which is z equal to minus half x prime sigma 1 inverse minus sigma 2 inverse x plus mu 1 prime sigma 1 inverse minus mu 2 prime sigma 2 inverse into x again. The first of these two terms on the right hand side is a quadratic in x, whereas the second term is linear. So overall the z function, unlike in the previous case, is a quadratic discriminant function. And if you note that if the two sigmas become equal, the quadratic term actually vanishes and you go back to the previous linear discriminant function as a special case. So the linear discriminant function is a special case in the sense that it assumes the two variances are equal. If the two variances are not equal, then the discriminant function is quadratic by nature. In this case again, as before, if the parameters are unknown, replace them by the corresponding statistics. Now let's go back to the example, and if you use the quadratic discriminating function in this case, you see that the straight line we had before now gives you a curve. Okay. And this curve actually does a better job in the sense that, unlike previously, in this case we just have two misclassifications in the sense that there are two red A's. So all of the non-admitted are in the non-admitted group, barring these two red values here in the middle. All of the admitted are in the admitted group. Previously, when we were using the linear discriminant rule, we had three misclassification. So in this case we could decrease the misclassification probability somewhat and get a better rule. And you also get this basically is because instead of a linear function or a straight line, you are using a curve, and hence is able to include more of the A's without including the N's into the blue group. Now when you do a classification, the question arises is how good the classification rule is. One way to judge classification rules is to look at the misclassification probabilities. As we saw in the previous examples, the smaller the number of misclassifications, the better it is. So what we need to do here is we need to find the smallest value of the total probability of misclassification. Remember that it is given by P1, the prior probability for the first group, into P2 given 1, probability of misclassifying an individual from the first group into the second, plus P2, which is the prior probability for being in the second group, into the probability of misclassifying an individual from the second group into the first group. and we need to find the smallest of this TPM values. This is known as the optimum error rate or OER, and we have seen in the last module that this is given by the ratio of the two densities being greater than or equal to the ratio of the two prior probabilities. Mind you, the cost is not involved here and therefore are taken to be equal, and the complement set of R2, which is just the complement of the first set. Now if you look at the TPM for normal populations with known parameters, P21 given one is probability of the discriminant function P minus half of the remaining term, which is the constants, greater than or equal to log of P2 by P1, and given the condition that the individual comes from the first group. This on simplification would lead to probability 2 given 1 is phi. Now phi is the notation for this, is basically the distribution function of the standard normal distribution. It comes out as phi of 1 by root over delta log P2 by P1 minus root over delta by 2, where delta is mu1 minus mu2 prime sigma inverse mu1 minus mu2. So delta is basically the distance between mu and mu2 normed by the variance. So we get a very simple form in terms of the standard normal distribution of the probability of misclassifying an individual from the first group into the second group. Now similarly, if you look at the other probability of misclassifying an individual from the second group into the first group, this is given by phi is minus 1 by root over delta log of P2 by P1 minus root over delta by 2. And this 2 leads to the OER, which is P1 into the probability of 2 given 1 plus P2 into probability of 1 given 2, and this would be the expression for the OER. The smaller the OER, the better would be the rule. Okay? And if you look at the OER, this gives you how good your classification rule is. In this module, we have discussed how we can identify two groups defined by two different normal populations. The normal populations may have known parameters or unknown parameters, and the discriminant rules can be formulated in either of these two cases. We have found that when we have the two variances of the normal populations equal, then we get what is referred to as a linear discriminant function. When these variances are different from each other, this leads to what is referred to as the quadratic discriminating function. We have also looked at criteria of judging whether the discriminating rule that we have found out is good or not. In further modules, we'll be looking at some of the other distributions as well as into problems where we have more than two populations to group into.